Let me close the door. Good morning, everyone. So let us start our exercise class. So this exercise class will be dedicated to the notion of the flow of probability and how this flow of probability looks for specific cases, and in particular for a case where we have a potential step. So for which you already saw the solutions for the wave function in the lecture. But first, before we talk about this particular example, let us just start with how we define the flow of probability. So consider a particle which is governed by Hamiltonian H, which our usual free particle Hamiltonian part, which is p squared over 2mu, where mu is the mass of the particle, and it is also subject to some potential v of x. And so v of x, if we write it in its matrix form, what we get is this integral from minus infinity to plus infinity dx. Its function v of x and CAD pro x. And so what we are going to look at, the property we're going to look at, the probability of finding a particle in a space region from A to B. So when x belongs to AB. And we will look how this probability changes with time. So we'll have some probability of the particle being in this interval AB, which of course depends on the state the particle is in, and the state in its own turn is dependent on time. So this whole thing will also depend on time, and we'll see how it changes. Okay, to do so, we first need to calculate how the probability density changes. And then we can just integrate that probability density and essentially get our probability to find a particle in the interval AB. And so if you look at the probability density, what we mean by probability density is just the probability of finding the particle in this particular point X. So it's just the probability of finding particle at the point X on this real line, which depends on the state, of course. And this is just given by the modulus squared of the wave function. And the first thing that we're going to show is that this is how this probability density changes with time. So for this, we just need to take the derivative, the partial derivative of this density with respect to time t. So we see here that in general, this probability density depends on x and t because it's given by the square, modular square of a wave function, which depends on x and t. So here we just take the partial derivative with respect to t. So basically, we need to calculate the time derivative of this object here. So for simplicity, let us just write, yes? Oh, here. Here. Yes. Okay. So the question is, what's this label means here? Yes. Yes. So this is just, so I mean, this is a function, right? So basically, when we calculate the probability of parting particle in this interval, it depends on what is the wave function, what the wave function is at that point of time. So I'm putting the t here to emphasize the fact that this is a quantity, this is a function which depends on time. Because the wave function depends on time. So this is just a notation where I emphasize that this is a function of time, and here I'm just specifying when on which state is calculated. No. I mean, because here we introduce the t as the parameter which represents time, right? So basically, then we say, oh, we calculate this probability on the wave function psi of t. So this probability depends on t. Yes, but I mean, like, this is just my notation. I can also just drop this as long as you understand that this is an object which depends on time. It's fine. So here I'm just putting this t here to emphasize the fact that, for example, we can take the derivative of this probability with respect to time, which we're going to do a bit later. Okay. So basically, we take the partial derivative of this probability density, and we arrive to the partial derivative of this modulus psi squared. And here we rewrite this as a partial derivative of the object, which is psi of xt, psi conjugate of xt. Because this is just follows from the fact that for the complex number, its modulus squared, you can just write as z by z conjugate. And here we apply the taking derivative by parts rule. So basically, this is equal to deep psi dt psi star xt plus d psi star xt dt psi of xt. So now we have these two objects, which are just the derivatives of the wave function with respect to time. And we know how to calculate this, or which equation would give us these derivatives, which is the Schrodinger equation. So for example, to find this, we just write the Schrodinger equation, which is IH bar d psi xt dt equals h psi xt. And h we wrote here. So this is the Hamiltonian the particle is subject to. So this is the usual part, p squared over 2 mu plus the potential. And we have the our wave function in the position representation, which means that for this case, p acts as ih d by dx, I think with a minus, and basically then p squared over 2 mu, its action can be written as minus h squared over 2 mu d2 by dx squared. So then, and the potential depends on x, and we have the position representation, which means that it just corresponds to this function v of x, multiplying the wave function by this v of x. So basically what we get here is minus h bar squared over 2 mu d2 psi dx squared. So the second derivative with respect to the position, plus v of x psi. Yeah, and psi depends on x and t. Okay, so this was just the derivative of the psi. Now we need to write the derivative of the psi star, which we can get by just taking a complex conjugate of this equation. So let me maybe like this away and just write it on the. So what we would get is minus I h bar d psi star dt equals minus h bar squared over 2 mu d2 psi star dx squared plus v of x psi star. Okay, so now we can express d psi, so derivatives of the psi and psi star with respect to time. So so basically what we need to do there, we just need to divide both sides by I h bar. And then we get the following, that d psi dt equals IH over 2 mu, because here we get that minus 1 over I is just I. d2 psi star dx squared minus I over h v of x psi. All right. Yeah. Okay. And d psi star dt is equal to minus IH. Sorry. So here it's without the star, because it's just psi. So d psi star dt is equal to minus IH over 2 mu d2 psi star dx squared plus I over h v of x psi star. So these are, we got just from analyzing the Schrodinger equation. And now we return to our derivative of the probability density. And now we just plug in these derivatives into that equation and see what we get. So d of dt, probability of x, and the state psi of t equals, so first we plug in this, IH over 2 mu d2 psi dx squared minus I over h v of x psi, and everything multiplied by psi star minus plus what we have there is d psi star over dt. So we plug in the second line, minus IH bar over 2 mu d2 psi star dx squared plus I over H bar d of x psi star, everything multiplied by psi. So we can massage this equation a bit. So what we see here is, for example, this term here and this term here, they cancel out. Because here we have, basically what we have here is IH over H bar V of x modulus psi squared. And here we have the same thing. So we are only left with these two terms, the first term in each bracket. So what we get is IH over 3 that we can take out. So even let us take out minus IH bar over 2 mu. And what we're left with is d2 psi star dx squared psi minus, so this was the first term here, minus this term, which is d2 psi dx squared psi star. Okay, so for now we arrived to this equation for the rate of change with respect to time of the probability density to find the particle at the point x. Okay, so now to give it a kind of a meaning, we can also introduce something that we will call the probability flow, and we'll see why. So the probability flow is defined as J of xt equals IH bar over 2 mu d psi star dx psi minus d psi dx psi star. It looks very similar to what we just got here, except that there's first derivatives. So then the next thing that we'll show is, let us take the derivative of this j with respect to x. So basically, the rate of change as we of this quantity as we move along the x-axis. So let us just consider gj over dx. So this stays IH bar over 2 mu. Now we take for each of them a derivative by parts. So first we take the first component here, d2 psi star dx squared psi plus d psi star dx d psi dx minus second component here. So first we take the derivative of the first component, d2 psi dx squared psi star minus d psi dx d psi star dx. So these two elements in the sum all cancel out. And what we arrive to is something we've just seen. So it's IH bar over 2 mu d2 psi star dx squared psi minus d2 psi dx squared psi star. So this was dj over dx. So this is up to the minus here. This is the same equation that we got here. So basically then what we can do we can just say that the rate of change of the probability density with respect to time is equal to the minus the rate of change of this probability flow. And this is kind of one of the standard equations you see in classical physics as well. So this is something that is called a continuity equation. So for example, in electrodynamics, you can write the same equation for the charge and current. So imagine, I don't know, imagine some surface, and inside the surface you have a certain electric charge, and then there is also a current going through that surface. And of course, the rate of, and the current represents the rate of how charge is going out of this surface, basically. And then of course you need to have this continuity equation, which basically says, oh, the rate of change of the charge inside the surface should correspond to how current flows out. And here we have kind of the similar thing with a probability flow. So what we get is that the rate of change of this probability density is equal to minus dj over dx. Okay, so now let us come to the original question that we asked. So we consider the rate of change of probability to find a particle in the interval AB. So not in a particular point of x, which of course depends on x, but the probability to find it in an interval AB. So how do we calculate this probability given our probability density? Yeah. We need to write the integral, right? Yeah. So the integral from a to b dx, the probability to find it in x given the state psi of t. Right? So now what we want to see, what we want to calculate is the d by dt of this object. So because here I take the integral over the variable x, I can just, to take the derivative, the integral, I can exchange the order of derivative and the integral because they're taken over different variables, and just write that this is, we take the integral over dx, but before that we just take the time derivative yeah, and here will be already partial derivative because probability depends on x and t. But this object we just calculated, we know that this is equal to minus dj over dx. So basically we can write that this is equal to integral from a to b dx minus dj dx, but at time t, at a particular time t. So then here we're just integrating a derivative over x, a derivative of something with respect to x. So basically, we just get the values of this function j at the points at and bt. And this is with the minus, so I have to exchange the order. So this is just j of at minus j of bt. So basically, how you can see it is, so we have our line, right? Our real line, which corresponds to the positions of the system. And then we are calculating the probability to find the particle in this interval. And then imagine that the probability itself is a flow. So basically, at the point A, it corresponds to the flow g of at. And at a point B, there is a flow g of bt. Basically, everything that stays in this interval, or the probability that stays in this interval, exactly corresponds to the difference between these flows. So basically, this is all that went in but didn't go out. And it's the same, like you can think about it like in electrodynamics way with the currents, or you can think about it, oh, there is a flow of water. And then you need to calculate, for example, what is the mass of the water, which is contained in this portion of the tube. Then then basically what you need to calculate are these flows and then take the difference. Okay, so now for an actual example of this, we can take an example of a wave function, which is a wave packet. So basically, then the psi of x can be written as the envelope phi of x, and then the complex exponent e to the power ikx, which corresponds to the movement of the packet. Yes. Yes. Sorry, how did we?
So there we have d delta t from using x.
Yes.
And integrate over x. And the step is
okay, so what happens here? The first one. Yes, so we so we have the probability density. Then to find the probability, so to find the sum, the total probability for the interval between a and b, we integrate from a to b with respect to x, this function. Yes. Then we want to find out the rate of change of this probability. And the rate of change of this probability is basically the time derivative of this function. And basically we take the time derivative of this integral, right? And because we take the integral over the x and not t, we can exchange the order. So basically what the first thing that you would write is, oh, this is the time derivative of this object, right? But because we take the integral over x and this is over t, what we can do, we just say, oh, I exchange these two things and I just take the time derivative of the function that I'm integrating. And then after that, I'll integrate whatever I get over x. So this is just a simple mathematical rule. So when you have a function of many parameters and then you integrate over one, but you also need to take a derivative over the other parameter, you can always exchange these two things. I mean, of course, there is a caveat as in, so for example, this to the limits of integration. So they don't depend on t. So for example, if they would depend on t, this would be a slightly different formula. But for now, but because we integrated over a set interval, then we can always exchange these two. Okay, so now this was all kind of theoretical. So let us apply this this notion of the probability flow to this to the notion of the wave packet, where we have like you can imagine that this is kind of this envelope function phi of x, and then it's moving because we have this propagator e to the power I kx. And let us calculate the probability flow for this wave packet. So, so here, what I mean by we have this wave packet, I'm just saying that suppose that we're considering this wave function which changes in time, and then at some point in time we see that it has a form of this wave packet. So I'm just calculating the probability flow depending on x at that fixed point in time. So j of x is equal to, I'm just rewriting, it's I h bar over 2 mu d psi dx psi minus d psi dx psi star. Okay, so I'll leave the calculation for your homework because it's also in the exercise sheet. So first you just need to find d psi dx by just taking a derivative by parts of this equation, then d psi star dx, just taking a complex conjugate. And also another constraint here is that phi of x is real. So the envelope function, we consider it to be real for this case. Okay, and then the answer that you would get, you would see that you actually maybe could have guessed it from the beginning, because what you would get is h bar k over mu, and then phi squared of x. So what is phi squared of x here? So phi squared of x is just the probability density, because if you take modulus psi squared, this would exactly correspond to phi squared of x. And what is this? What is this object here? It's the following. So if you calculate the momentum of this wave packet, you would get h bar k. So this was already thing done before. Like for example, when we were considering the Gaussian wave packet, you could see that the momentum would be given by simply this coefficient in this part of the wave function e to the power I kx. And mu is the mass, and when we divide momentum by the mass, we just get kind of a classical velocity. So if it's like, oh, I take the average momentum of the packet divided by the mass, I get the average velocity. So basically here, what we get is that this flow can be just given by the probability density of finding the particle at the point x multiplied by its classical velocity, which corresponds to the usual definition of the flow. So for example, yeah, basically, if you consider a flow, for example, water, which is going through this pipe, so this is the mass of water per unit time, and then the mass of the per unit time, the dV, the volume of water, would be S, which is this cross section of the tube, the velocity of the water V, dt, because in the dt time, the water would go this far along the tube. So, and then dm by dt, which is how we can define the flow, would be rho v dt, which would be proportional to this velocity. So dt would go away. So if this is confusing, just disregard it for now, but just keep in mind that, for example, for this classical current definitions in hydrodynamics or electrodynamics, you would get that it would be proportional to the classical velocity of water or the electrons going down the cable. And here we kind of intuitively get the same thing because we're considering a wave packet, which is on average going with that velocity, hk bar over mu. Sorry, h bar k over mu. Okay, so okay, we have a bit more time. So I'll already start with looking at the flows in the K. Yes.
So this J is not
So the K is not in the Hamiltonian.
no, but JX is not dependent on Hamiltonian.
So it's dependent on the wave function you're considering, right? So basically and then the wave function is the solution to the Hamiltonian, right? So in a sense, it is not dependent on the under which potential we write it, but it's dependent on a psi, right? So it's dependent on a wave function, and then for different Hamiltonians, you would have different solutions of the wave function, right? Does this make sense?
Yeah, but this portion is not dependent on G.
Yes, that's something I made a comment in the beginning that so suppose that we're looking at the wave function, which evolves in time, and then at some point we stop the time, and we see that at that point in time we are looking at the wave packet. So I'm just not writing it here because so it's just particular point in time, so that parameter is fixed. So time t is fixed for this example, and it's just at that time t we have this dependence on x, and we calculate the probability flow. Yeah. I'm sorry, I didn't understand.
Like this JX that we calculated here.
Yes.
Which is essentially the same thing as the derivative of probability. Is independent at which time for probability. So the derivative of probability for motion wave packets is not dependent on time. Because can you
Yes, I mean, so for the Gaussian wave packet, because it's always a Gaussian wave packet, for the Gaussian wave packet, this part would change, right, with time. So in that sense, implicitly, this would depend on time. So if you take a particular example of the Gaussian wave packet, you would have that kind of as it moves further, the envelope gets more spread out, right? So basically, you would have dependence on t here.
Oh, because
Yes, but in a sense, like this will always be a Gaussian, just with a different spread parameter. Make sense? Okay. Okay. So now we have some time to just state our next problem we'll be looking at. So we'll be taking the particular potential, which is the step potential. And in a lecture, we already seen like what are the solutions in this case. And we also even defined the reflection and transmission coefficients. And now we will do the same, but keeping in mind our definitions of the probability flows and calculating the probability flows for the wave function on one side of the step and on the other side of the step. And we consider both reflecting and scattering solutions. So what is our problem, basically? So we have, let's say this is the of x, this is x. We have a step potential, which means that for the, so v of x is 0 for x smaller than 0, and v0 for x, let's say this, for x bigger than 0. Okay, and in the lecture, I'll write out the solutions again here. So we consider two situations. So the first situation is when the particle has energy, which is less than the step potential. So these are the deflecting cases. So we're reflecting, so suppose that we have the particle incoming, then part of it reflects, and also, but some of it goes into there's some probability to find it for the x bigger than 0, even though the energy is less than v0, but this probability is exponentially decaying as x goes to infinity. So here, the solution would be just the exponential decay. So these are reflecting states, and for these states, the solution we can write the following way. So here, on for the x below 0, so before the step potential, this is just a combination of the incident and reflected waves. With a different, so it's just a linear combination of them with different coefficients. And for the x's which are above 0, we just have the decaying. So this is x less than 0, and this is x bigger than 0. Okay, and then the second option is when the energy of the particle is bigger than B0, so it's above the potential step. In this case, we also have the transmitted wave. But this is only for energy bigger than V0. And these states are scattering states. So here we write that this is for E less than V0. We have decay. So, but here we just have the following. So A e to the power I k on the left side x plus b e to the power minus I k l x. And here we just have c e to the power I k r x plus d e to the power minus I k r x. But for the cases we'll be considering, we're interested only in the case where d equals 0. So we will not take into account this this term. So we just assume that d equals 0. To just have the case when we have the incident wave coming in, it's either reflected or transmitted. Okay, and I also didn't write how these coefficients k, b, k, l, and k, r are connected to the parameters of the problem. So k here is equal to just square root of 2 mu e over h bar, and b is equal to square root of 2 mu v0 minus e over h bar. And here for KL, we have the same thing for K, because basically it's the same, they correspond to the solutions of the same Schrodinger equation in the 0 potential. So KL is square root of 2 mu E over h bar, and KR is square root of 2 mu E minus V0 over h bar. Okay, this is the problems that we will be considering. And here we'll be calculating the probability flows for x less than 0 and x above 0. But I think we'll do it after the break. So now we have the break, and then in 15 minutes we'll continue. Yeah, so addressing the integral rule. So I was just confirming. So in general, it's called Leibniz integral rule, and it's basically for the integral where you integrate from a of x to b of x function, which is f of xt dt, and then you want to take a derivative with respect to x, basically. But you can look it up. Yeah. I mean, sometimes can be useful also in the cases where like the limits of integration depend on the variable. And then, you just add a specific term there. But USB-C?
Yeah.
Yeah.
Anything more powerful than this? Does it
No,
work for
that's,
laptop?
yeah, it was for laptop. Okay, shall we continue? So yeah, now let us calculate stuff. So first we will calculate the we'll consider the reflecting states, and we will calculate the probability flow for x less than 0. So for x less than 0, we have that psi of x is a e to the power ikx plus b e to the power minus ikx. Okay, great. Now j for x less than 0. So again, our formula, IH bar over 2 mu, d psi dx, psi star dx psi, minus d psi dx psi star. Okay. So what is d psi dx? Well, this is I k a e to the power ikx minus I k b e to the power minus ikx. And then we take just the complex conjugate of this expression, and we get the derivative of psi star. So we get as minus ik a e to the power minus ikx plus ikb e to the power ikx. Okay, divide this. And now we just plug it in into the expression for the probability flow. While I'm erasing stuff from the board, you can already start calculating it. And actually, let me correct myself, because there was a mistake. When we're like an inaccuracy. So when we take the complex conjugate here, we also have to take the complex conjugate of A and B, because A and B are not guaranteed to be real numbers. They can also be complex numbers. Okay. Also, you can think about why I didn't include any dependence on time for this when considering this solution.